Okay, now we look at the top of page 82 and we look at problem number 1. It says in Newton's law of universal gravitation, we were told that G is a constant. Look carefully at the equation that describes gravitational attraction. Describe the relationship between the gravitational force between two objects and the distance separating their centers. If the distance goes up, what happens to the force? What if the distance goes down? Now listen, this is all according to fractions. Now, if you look at the typical fraction, let's say our numerator is 5. We would take two fractions. So in our first fraction, let's say our denominator is 9. And in our second fraction, our denominator is 37. Now, if we take out our calculator, because we want to see what happens when your denominator gets larger. So when we take out our calculator here, let me see. Oh, that comes out pretty well. Let me turn it up a little bit. Okay. All right, now, when we type in 5 divided by 9, and then 5 divided by 37, if you notice here, the size of the fraction gets smaller. Now, in relating this to the lesson that we're talking about, they said describe the relationship between the gravitational force between two objects and the distance separating their centers. Now remember, with that formula, the formula is F is equal to G times M sub 1 times M sub 2 all over R squared. So the distance is the denominator. So as the denominator increases, the gravitational force decreases. As the distance decreases, the gravitational force increases. So basically we could say if distance goes up, the force goes down. If distance goes down, the force goes up. So there's an inverse relationship here. Now we come to problem number 2. Repeat question 1, but this time describe the relationship between the gravitational force and the mass of the first object M1. Now if you notice, M sub 1 is in the numerator. So what happens with the fraction in the numerator, you could take the same denominator. Let's take the denominator of 50. Okay, now if our numerator was 1 and then our numerator became 49, let's take a look at this in a calculator. 1 divided by 50 and 49 divided by 50. Now if you notice here, it got significantly larger as the numerator increased. So basically our relationship goes like this. If the mass increases, the force increases. If the mass decreases, the force decreases. So they have a direct relationship. Now we look here at number 3. Why can you feel the gravitational attraction between you and the earth, but not between you and the person sitting next to you? Notice that I said gravitational attraction. Refer to your answer to question 2. Now remember, if we're looking at the mass, the person next to you does not have the same mass as the earth. So a person is much smaller than a planet. So you cannot feel the gravitational force. Now, it says, why can you feel the gravitational attraction between you and the Earth, but not between you and Jupiter? Okay, now this refers back to question number 1. Now, Jupiter, I believe, is the largest planet, if I'm not mistaken. But the problem is, it goes back to number 1, that the distance is so far away, so that takes down the gravitational force. So even though Jupiter is bigger than the Earth, Jupiter is too far away. So you can't feel the force. Okay, now it says the force of gravity between the Earth and the Sun is strong enough to keep us in orbit, because even though we're about 149,597,870,700 meters apart, the mass of the Earth is, now this is an extremely long number here. That is an extremely long number. And the mass of the Sun is, now this is even longer. If you're like most people, including me, so don't feel bad, you have no idea what those numbers actually mean. They're just too big to get any perspective on them other than, wow, those are really big. To make it easier to understand and work with numbers of ludicrous size, we'll use a clever method for writing them using exponents. Consider the number 300, which can be written as 3 times 10 squared, which of course is 3 times 100. If you're thinking that's silly, hang in there. There's a point. Take a look at the first handful of powers of 10. Do you see the pattern? Each extra power of 10 puts another 0 on the decimal equivalent. In fact, the power indicates exactly the number of zeros included. Here's why this is helpful. 5 billion is a tremendously large number, which we see here. Notice that there are 9 zeros. So we could write 5 billion as 5 times 10 to the 9. Much shorter than writing out the 5 billion, which is more concise and easier to read. If that makes sense to you, then you understand the idea behind scientific notation. Now, we need to move on to page 83. Now it says, writing large numbers in scientific notation, write a decimal point at the end of the number, then move it left so that there is just 1 digit before it. Now, when it says here 1 digit before it, the digit must be 1 to 9 inclusive. That means that the digit you have behind the decimal cannot be less than 1, but it cannot be greater than 9. Now it says multiply the result by 10 to some power will be the number of places you move the decimal. Okay, now we move down here to questions 5 and 6. It says for questions 5 and 6, write each number in scientific notation. The number of people in the United States in November 2015 was 322,146,000. So what we would do is this here. We would look for the decimal. When you don't see a decimal, it's assumed to be at the end of the number. So we will move that decimal until we have 1 digit in front of it that's between 1 to 9, and that means that it could be 1, 2, 3, 4, 5, 6, 7, 8, or 9. So we will move this decimal. We moved it once, twice, 3, 4, 5, 6, 7, 8 times. So it'll be 3.22146. We do not have to add those last zeros. Then times 10, because we have to multiply by 10 for scientific notation. And we counted how many places we moved, which was 8. So the exponent would be 8. Now we come to number 6. The distance in miles from Earth to the moon, we have 238,900. Again, we start where the decimal is. It's behind this number. So we move 1, 2, 3, 4, 5 places. So it'll be 2.389. We don't have to write the last two zeros, times 10 to the 5th power. Now we can also use scientific notation to write very small numbers using negative powers of 10, which we see here. It says this time the pattern is that when the negative exponent gets larger by 1, meaning more negative, the decimal point slides one spot to the left. For example, 0.03 is the same as 3 times 10 to the negative 2. So in keeping with what we talked about earlier, we will move this decimal 1, 2 places to the right. So that will leave us 3. And then times, but since we moved it to the right, the exponent would be negative 2 instead of positive 2. Now it says write in small numbers in scientific notation. Move the decimal point right so that there is just one non-zero digit before it. Drop all zeros that come before that digit. Multiply the result by 10 to some power. The power would be the negative of the number of places you move the decimal. Now we're going to apply this on page 84. It says in question 7 and 8, write each number in scientific notation. The weight in grams of 1 grain of spruce pollen is 0.00007. So we have to move this decimal until we get it behind the 7. 1, 2, 3, 4, 5 places. So it'll be 7 times 10, and since we move 5 to the right, it'll be to the negative 5 power. Because remember, the number that's in front of the decimal, and remember it's assumed to be a decimal behind the 7, must be either 1, 2, 3, 4, 5, 6, or 7, 8, or 9. And 7 fits that bill. Now number 8. The average number of hours it took the U.S. government to spend $1 million in 2012. Now we look here. We know we're going to have to move the decimal to the right, but we will move it 1, 2, 3 places. And that will give us 2.1605. And that would be times 10, and we moved it 3 places, so it would be 10 to the negative 3 power. Now what we're going to do, we're going to go to the opposite. We're going to go from scientific notation to decimal notation, which is described down here, and I think it'll be better once you get an example. So let's go right to the example on page 85. It says write each number in decimal notation. Now decimal notation is the regular way we write numbers. So basically they want us to change this from scientific notation to a regular number. So it says the number of drops in a gallon of water, we have 9.085 times 10 to the 4th power. So now, since this is times 10 and the exponent is positive, we would take this 9.085 and we will move it to the right 4 decimal places. 1, 2, 3, 4. So this will give us 90,850 drops. And please do not forget to put the units behind your answer. Now B, the mass of an average dust particle is 7.53 times 10 to the negative 10 grams. So what this means is, since this is taken to the negative 10 power, that means we would take this 7.53 and move it 10 places to the left. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the decimal will go here. So it'll be 0.000000000. And then we will write it here. It'll be 0.00000000753 grams.